Oh, sorry. Hi, I'm Paul from GFI. Most of my supervisors are also from GFI, and one from IMR. So in some ways, I have a slightly difficult task in that I need to make my talk as exciting as South Africa or these seaweeds from beautiful fjords. Yeah. So I will be talking about identifying things that are difficult to identify. I had some fun with the title, but I didn't manage to find a particularly clever one. So I wanted to talk briefly about what ecological regime shifts are. And then, because the subject is a little complicated, we're going to dive down into just one of the problems we face, or I faced, when trying to figure out where these ecological regime shifts have happened in the past, and how I've dealt with this. We can think of regime shifts as this decreasing of a system's resilience. So Juan talked about some of the stressors that ecosystems can face. They have increasing temperatures and decreasing salinity. And even though these effects from, caused by climate change happen very gradually, they can result in very sudden changes in an ecosystem's action. This can be sudden increases in chlorophyll, which sometimes happens in the Baltic Sea, or a change in the dominant species of an ecosystem. And this change in a dominant species of plankton can be amplified through the food chain and sometimes affect what fish are around. So this repeats that slightly, but yes, the most important changes that a regime shift can affect are this accumulation of chlorophyll in the sea surface, which can have implications for fisheries and also affect the ocean's ability to act as a carbon sink, which is, important for important for how much climate gases are going to be in the atmosphere, they kind of directly affect these three sustainability goals of zero hunger and climate action and life underwater. So this is an example of a time series of plankton from the North Sea. On the top, we have this PCI anomaly, which is kind of analogous to the amount of chlorophyll in the water. And it changes over time in that sometimes there's lots of green stuff around and sometimes not so much. And then the second two are both phytoplankton species and the bottom two are zooplankton species. It's kind of difficult to look at these time series and decide whether or not the changes that we see over time are just random variations or if they're emblematic of a more extreme shift in the entire ecosystem, which is what I've been working on. So when we think about the kind of random changes that can affect things, we can divide these random occurrences into what we call red or white noise. Using the example of the board classic Yahtzee, we can think of white noise as a completely random change. So even though you have, if you're trying to get 5 of the same dice roll, you might think if you've already got 4, you're probably definitely going to get the last one, but it's still a 1 out of 6 chance, or a 5 out of 6 chance that you're going to lose. So it's completely random. But red noise can be more illustrated by this drunk man walking down a road. So he's kind of shaking around. He doesn't know what side of the road he's going to be on, and he doesn't know how long he's going to be on that side. So he's going first on the left, and then a dramatic shift to the right, and then another dramatic shift here, and then he gets completely lost. So we can talk about red or white noise. So I guess the red noise would be blood, because he's falling over, or white, because of the dice. So when we look at these graphs I have before, they're systems where red noise is much more prevalent. And red noise is really, it's realistic in that we see it a lot in nature, but it's really difficult to model in a statistic way, because a lot of the assumptions we use for normal statistical tests are violated by this red noise systems. And that's why a recent paper has found that previous models looking at the identification of regime shifts in the past have kind of found that a lot of them have very high rates of false positives identifications. So you can talk to me later about how what method I used to get around this, because it's running out of time now. But basically, I discovered this, or I found this method, and it's much better at reducing the rates of false positives. On the top, there's slightly less than 20%, or 5, or less than 5. And these are different sample sizes of simulated species that I've made up. And so my model is predicting the percentage chance of a regime shift happening or having happened over the past 70 years. So on this bottom one here, we can see there's a very high chance of a regime shift happening between in the late 80s or early 90s. And here it's more earlier. So these graphs represent different areas of the North Sea, and that's kind of what I'm working on at the moment. First, I'd like to thank Seas for having me here so far. It's been really great interacting with experts from lots of different fields. You've listened to some of them already. Yeah, and yes, it's given me lots of opportunities to share what I'm thinking of as well. Yeah, my project here, or my contract will finish in May, and I guess I'm looking for steps. So if you have a job opening, send it, please. Thank you.